it first if you have confidential stuff, for example, but try to be as close as possible to code, to production data. And honestly, often the hardest one is to be close to production infrastructure, because it's going to depend on where you work, on your company, obviously, but not all companies have the money to have the benchmarking environment that's exactly the same as your production environment. Like, it can be prohibitively expensive, but again, try to choose the proper, as close as possible. I'll have a few examples later of benchmarks that gives different results depending on which machine runs them. And finally, especially if you're using non-dedicated hardware, like running on your local computer, run the benchmarks multiple times. Because sometimes you're just going to see a difference, and when you run it another time, it's completely disappeared, because the difference just happened to be that something was running in the background at the same time you're doing your benchmark. So run them multiple times and check they're coherent. They're consistent, I mean. And, well, once you've benchmarked everything, it's time to implement, only if you think you're winning something that's worth it. Because destroying everything behind you is not a good idea. You're going to have to maintain that code, and sometimes just optimizing early for something not big, it will prevent you from doing a bigger optimization later, because your code will have become so unreadable, you won't be able to figure out something. So make sure what you're doing is worth it, and then you're back to monitoring, because as I said, sometimes the benchmark is not representative of what happens in actual production. So once it's implemented, once it's back in production, you monitor again to make sure that, hey, it worked. A bit of on theory. I'm not saying theory is unimportant. It is important when you want to optimize, because that's where you're going to have your ideas about what you can improve. However, modern systems are fucking complicated. Between compiler optimization, JIT optimizations, everything that gets optimized at the runtime, but also everything that gets optimized at the CPU level, makes for extremely complicated systems. You can have an idea of how they work, but honestly, at the end of the day, the only way you can get a proper picture is by experimenting. You have to benchmark, you have to monitor, you have to try it out. One point I like to bring a bit about this is what I call the big lie of the big O notation. Like, you learn at school, like, hey, logarithmic is better than linear, which is better than hyperlinear, which is better than quadratic, etc. That's wrong. That's not the case. Logarithmic algorithm is not better than a linear algorithm. The problem is, the big O notation, by definition, completely ignores constant factors, which means that it will help you figure out how your algorithm is going to evolve as you put more and more data into it. It's good for that. However, it's not going to tell you this algorithm is better than that algorithm. One of the biggest examples I like for this one is heap sort versus quick sort. Heap sort is hyperlinear in the worst case. Quick sort is quadratic. So quick sort on paper is worse, right? Except that for the past few decades, every single sorting function in every language has been implementing using quicksort. Recently, well, over the past few years, we've added more and more heuristics to make sure we're not in the worst case. But quicksort is just flat out better than heap sort for pretty much every conceivable use case, because the way it's implemented makes a much better use of its time. So yeah, beware of the big O notation. It's not going to tell you that algorithm is better than this one when you're comparing to very different algorithms. Before I jump into the very technical stuff, so my benchmarks have been done with Scala 3.5, SBT GMH, latest version, the Temurin JDK, version 21. All my benchmarks show durations, so lower is always better. And finally, you have the URL of the complete benchmark at the bottom if you want to get it. I'll put it again at the very end with a QR code, so don't worry if you didn't get it now. Okay. We're going to start very simple with just really basic iteration. I have the simplest function imaginable. It does literally nothing. It returns its first argument. And we're just going to run a for loop and a while loop. And I want you to just think for a few seconds, what do you think the benchmark will look like? So if you know Scala, which I guess most of you do, you know that a for loop is actually chaining flat maps and filters. So yeah, you'll expect the for loop to be a bit worse. It's not a bit worse. it's yeah, there's not just no comparison. The for loop is terrible. However, this is a very unfair comparison, right? Because my function does nothing, literally nothing. The runtime is going to optimize it out of existence. So I'm really comparing the loop time. So okay, while it's almost instantaneous, for takes some time. Okay, what happens when I do something? I've added a simple addition. Okay, still not a very complicated method. Okay, a bit more fair. And that's just an addition, right? If you start doing something like a multiplication or something really complicated, like a division, the gap between the two gets smaller and smaller. But still, simple additions is sometimes not much less than what you're doing, right? So I have done loops where I've been doing things that were just a bunch of additions chained together. In those cases, yeah, there's a difference between a for loop and a while loop. And by the way, if you're stuck with old version of the JVM or of Scala, it's way worse before, especially, actually, it's not even Scala, the main culprit, actually. The JVM got way better at optimizing. If you're on JVM 17 or even 11, it's way worse than this. However, Scala 3 came with something very useful, which is inline def macros, which very simple, because yeah, while loops are ugly, right? Nobody likes to write a while loop. So you can just write your very own C-style for loop in a macro, and you're going to get just exactly the same benchmark. And by the way, this is one of the cases where looking at the bytecode is useful, because if you look at the bytecode, you'll see that both using fast loop or a while loop has exactly, literally the same bytecode, to the point. But, okay, that's, you know, that's just basic iteration, right? We don't do that often. We usually work with collections. So collections is one of the data types we're going to use the most of all the basic data types, and it's probably the one that's going to impact your performance most. So let's start by iterating a collection. Will be a bit more complicated. This time we're going to do a function that calculates the square of the length of a string. And we have a collection of string, we just want to iterate on that. Multiple ways to do that, through functions. So you can just do a map and then sum. You can be smart and do a view before the map. You can do a fold left, for loop, while loop, recursion. And we're going to check this out on arrays, vectors, and lists. Again, just think for a bit, what do you think this would look like? Well, it's going to depend a lot on the size of the collection. So because this is simple iteration, actually the longer the collection is, the more time the runtime has to optimize. The first interesting thing to note is that arrays are faster, actually. If all you care is CPU performance, yeah, an array is faster. And please note that this is an array of strings, which is actually not the best use case for arrays. If your array contains, your collection contains basic types, ints, doubles, whatever, arrays are lightning fast. No heap, all on the stack, and the CPUs are really, really, really good at optimizing calculations on arrays of small primitive values. Another interesting thing to note is that the view does not actually help on arrays, and it doesn't even help that much. But obviously, this is not a great use case for Vue because there's only one function application before the reduction at the end. Other than that, well, fold left on small iterations is not great. Not great. The for and while loops are doing better. On bigger, when the collections, when the JVM has the time to optimize, it gets pretty much the best one, right? Main takeaway, yeah, arrays are fast. The smaller the collection, the better, but arrays are fast. Something else we often like to do with our collections is just, aggregate things as we go. So not much. I thought I'd throw this one in because, again, this was something that was actually pretty different in Scala 2. Because in Scala 2, prepending was actually significantly faster on list buffer than on list, for some reason. On Scala 3, as you would expect, appending to a list is pretty fast. Prepending, sorry, to a list is pretty fast. What I mean by appending to a list is obviously I prepend and at the end I reverse. I'm not prepending every single element because that would be terrible. There's no need for a benchmark for that one. I also compare it with Java's linked list just to have a basis. And yeah, Java's linked list, it's doing okay, but not great. Okay, nothing surprising here. Scala's better than Java. Yay. Okay, we're going to talk about sets. And we're going to talk about kind of the emblematic operation on sets, which is contains. For very small sets, arrays are good, actually. Just a simple basic array. And so here I'm trying about 1,000 lookups, 50% misses, 50% hits. An array is pretty good, actually. It's better than both Java's and Scala's hash set. Obviously, on very big collections, very big sets, it's going to be worse, right? But that's not the only one. Scala's hash set is slow. Scala's hash set is disappointingly slow compared to Java's hash set. I'm not entirely sure why, to be honest. There may be a number of reasons. It may be better optimized for other operations, like appending. Because remember that this is a Scala immutable set, while Java is mutable. Not entirely sure, but it's consistent across all machines. Scala's hash set are slow. However, we do have options if you want to optimize this. Sure, you can, go back to Java's hash set if you really need that, but there are a few alternatives, actually. There's something in Scala called a bit set. So a bit set, the basic idea is you're just going to have a set of ints. And to represent a set of ints, you can just use a bunch of numbers. With a single long, for example, you can represent a few ints by saying, hey, if int, n is present, well, the nth bit of my number is going to be flipped to 1, otherwise it's 0. And then my long is able to represent a short set of ints. Put a few longs together, and you're able to represent a great number of ints with extreme economy of memory and very good CPU performance. So, of course, this comes with two slight disadvantages. The first one is that your objects need to have an ID. Honestly, that's not that big of a deal, because a lot of the times already will, and if they don't, it's not that hard to have a pretreatment where you add an ID to everything. So, having the object have an ID is not hard. The problem is that, well, your set doesn't contain the values anymore, right? It's nothing more than a filter now. If all you need is a filter, that's fine. If you also need to pass around the actual values, you're going to need something else. Maybe an array. Obviously, if your set is a set of ints, just use a bit set directly, right? Don't even ask. We can, however, do even better. Array set is just a fancy wrapper as an opaque type around an array of booleans. And I'm just going to say, hey, my integer n is in the set if at the position n in my array I have boolean. That's lightning fast. Even better than the bit set, although with very large sets, it starts to catch back a little bit. Obviously, here there's another big issue, which is memory consumption is horrible compared to a bit set, especially if you have a sparse set, like millions of possible values, but only 4 elements, you're wasting a ton of memory. That might actually be worth it. And that's something I cannot answer for you, because that's going to completely depend on your actual use case. Maybe you really are ready to exchange like a few kilo or megabytes of memory to gain a bit of CPU. Okay, so yeah, just short recap. So bit sets, array sets, there are solutions, there are trade-offs. You need to have an ID, which is easy. You cannot get the value back, which means you might need another collection. And in the case of array set, the memory cost is terrible. What about maps? As you can expect, Java's hash map compared to Scala's hash map has pretty much the same issue, because, well, hash maps and hash sets are pretty much the same structure, actually, underneath. So, yeah, same issue. Scala's hash map are slow. Scala's hash maps are very slow. Again, you can have a solution as an array. Instead of having, if your keys have an ID, okay, forget about the keys. You're just going to store into your array the value at the ID of the key. Unlike a set, here the issue is more that, well, there's no real way to represent something missing from your array, right? Except if your type B is an option, okay, easy. But otherwise, you're going to need a default value. One big advantage of this, however, is that, again, if your values are primitive, like ints or doubles, this is going to be extremely effective because you're going to have an array of ints or doubles, again, all on the stack, super fast. And if you have missing values, well, you might want to resort to the old solution of, hey, I'm going to put -1 to denote a missing value. Yeah, it hurts as well, I know. But if you have an array of double, don't put an option, right? It's going to break all advantage you have just gotten by putting an array instead of anything else. Again, super efficient with a few disadvantages. And again, just as said, well, the keys are not in the map anymore. So if at some point you want the keys themselves, you're going to have to find another way to pass them around. Okay, so that was about our about collections. Let's go a bit into our own class structures, and we're going to explore what's probably one of the first things you learn when you do and try to optimize a bit. Well, one of the first things that you're told, I've heard a lot, is your class should be final. Because of course, if it's final, you know there's no polymorphism possible because it cannot be extended. So the compiler or the virtual machine is going to be able to optimize it a lot. Another pretty big difference is, am I going to do it as a mutable class or not? Yeah, I know, mutable case class, very ugly. So this is a basic statistics class. It's not that different from something we actually use at Datadome, also obviously very simplified. We're going to keep up a bunch of statistics for strings, and we're just going to iterate over a collection of strings, and for every string we're going to increment our statistics and get the results at the end. Okay, so I'll leave you just again a second. What do you imagine this would look like? Again, it's going to depend a lot on the number of iterations. This is completely going to depend on how hot the JVM is allowed to get on your iteration. On a small, first one thing to note though is that final versus non-final makes pretty much zero difference. And thinking of it, that's not that surprising because, well, that there is no subclass and that it can be optimized is something the runtime can figure out on its own. It doesn't need you to tell him, hey, this is final, there's no subclass. Yeah, it knows that. It has access to everything. So final, non-final, by the way, that does not mean do not put final. Final is still very useful just for type safety on your case class. But it's not going to have any effect on performance. However, for a small number of iterations, mutability, well, unsurprisingly, is doing significantly better because you're not recreating a new object every time. What's interesting is that for a lot of iterations, the difference pretty much disappears. It's very, very slight gap, a little bit better for mutability. The thing is, this is a very simple loop, and that's something both the JVM and then the processor are very good at optimizing. Because, well, even a human being can see that if all I'm doing is just, okay, copying the case class and, updating the stats, well, I could just reuse the previous object because the previous object is going to be thrown out, so whatever. That's something the runtime is good at optimizing. So it's going to optimize it. And in the end, I was honestly kind of surprised that it took it that long to figure out that it can be optimized. So, but that's not exactly fair, right? That's not exactly fair as a test for two reasons. One, because as I said, it's very easily optimizable from the immutable point of view. But it's also unfair to the immutable version because you're not taking any advantage of the fact that it's immutable. You're not keeping all the version of your stats. You're throwing it away every time. So let's try something different. Let's play a little game. Our game state is just going to be represented as our position in space, XYZ. We're going to be able to move around in all 6 directions. And we have a goal, that's going to be evaluated, giving on our current position, telling us, hey, how good are we right now? The immutable state is just going to, as usual, have an updated method returning a new move. And then the mutable state will have two methods, one to update the current state with a move, and one to reverse, actually, the change we just did. And what we're going to try to find out is, okay, I want to find the best possible combination of 4 moves to improve my goal. So obviously, it's a pretty naive algorithm on both sides. As a human beings, we could immediately see, hey, wait a second. If only the end position is what matters, a lot of moves combinations are the same, right? You could optimize this like, yeah, doing east, then west, then east, then west. Yeah, that's the same as right now. So there's no need to evaluate all of this. In both cases, I do the same, and it will do for that. Now, on the immutable part, it's pretty easy, right? I iterate over all possible moves. I have a new position. Then I iterate over all possible second moves. I have another position, etc. I do that 4 times. And at the end, I look at my end position. Is it better than whatever best position I've found until then? And if I found, I change it if necessary. All good, easy. The mutable versions is a bit uglier, because every time you've done a move, you've actually changed your state. So before you try another move, you have to revert what you just did. So you're constantly updating, reverting, updating, reverting, updating, reverting, etc. for the number of possible moves at the power of 4. And at the very end, because you've reverted everything, if you want to be able to output the actual target position, you have to reapply everything again. So obviously, it's not hard to figure out which code looks better. But regarding performance now, mutable's better, because, yeah, sure, you need to revert stuff, but even with the reverts, that's just a few variable assignments, right? And just a few additional variable assignments are nothing compared to creating new objects. What's more interesting is that going from 100 starting position to 1 million starting positions we're going to evaluate changes pretty much nothing to the ratio between the two. It's just doing a times 10,000 on both sides. Here, the JVMs appear incapable of actually optimizing the immutable out of it. In this case, mutable wins. Even though, again, that was a case where, well, there's some interest, right, in keeping an immutable object, because you're going to go back to that immutable object. Does that mean you should always go for mutable? Of course not. For example, if you want to keep a history of every single possible position in the past, then, yeah, if you're going to need those objects anyway, you might as well go with immutable and keep the old ones. But that's not that often the case, and most of the time, going with mutable is going to bring you some gain in performance. And yeah, I know it hurts. It breaks, potentially you're breaking a lot of type safety stuff, but again, is it a trade-off you're willing to make? And I cannot answer that question for you. Okay, all this was, until now, pretty, not basic, but just punctual improvements, just a slight changing here, changing there. What if we go really all in? We're going to rewrite our whole domain. So this is a very simplified version of what's happened inside Gaston to optimize the schedule. So I'm going to, I have a bunch of persons defined by just their ID and name. Topics have an ID and name. They also have a set of mandatory persons for RPG conventions, as that's the game master, of course. It needs to be on the game. A minimum and maximum number of persons. And your problems, the thing you're trying to optimize, is going to just be a set of topics, set of persons, and a bunch of preferences expressed by everyone. And in the end, you're going to get a schedule, which is, okay, here are my topics and the associated persons. Preferences, just a simple hierarchy. Preference is going to be a person, a topic. For example, for people to say, I want to play this, it's going to be a person, a topic, and a score. We also have the case of, yeah, two person are good friends, they really want to play together. Two others just cannot stand each other, there's no way they're playing together. All of those constitute preference, and to score a preference is pretty easy. You look into the record, you look if it's satisfied, and if it is, well, you have your score. You add all of that for all the records, you have your final score. Easy to read, easy to understand. Okay, how do we optimize now a schedule? So that's a pretty big chunk of code, but it's not very complicated. I'm going to go through all possible pairs of topics. So I start with an existing schedule. I'm going to go through every possible pair of topics. In each of them, I'm looking to all optional persons. Optional, of course, I don't want to remove someone who's mandatory. And I try, okay, if I swap them, is it better? And if it is, yay, I found an improved schedule. So that's just for swapping persons. Then I need another piece of code to check out what happens when you move persons without swapping them from one topic to another. That's a bit more convoluted because I need to check for that minimum and maximum values are still respected, but nothing too complicated either. In both cases, I stop as soon as I found a schedule that's better than the one I already had. Okay, pretty basic, pretty simple. Now, starting with a naive approach, as okay, well, I'm going to implement everything I've preached, right? Every single set that's just looking for content, I'm going to replace with array sets. Every single maps, I'm going to replace with array maps. A good thing, everything already has an ID. I'm going to use arrays as collection as much as I can. And I'm going to use macros, inline defs and such for doing loops and folds and stuff like that. Try to optimize as much as I can. And I get an improved version, which is so significantly faster on this machine. Doing the exact same benchmark on another machine that was less powerful led to actually pretty much no improvement. Very same benchmark, and the results were consistent. Multiple run of the benchmark, different machines. In one case, the significant improvement, the other, nothing. So again, yeah, try to be as close as possible to the production if you can. However, we can do better. Because, okay, who the hell cares about maintainability? Who the hell cares about having readable code that you can modify? None of those fancy schmancy object stuff, okay? Arrays everywhere. We might have somewhere the names of the person and topics so that we can output something readable. But for actually improving, we're going to work on only arrays. So I won't have an array of topics. I will have an array of, well, all the topic IDs, another array for all the topics minimum value, then another array for all the topics maximum value, same for the persons. And now the preferences, instead of being a set of clean hierarchy, letting me clearly see what kind of preferences exist, it's a bunch of matrices. And okay, so my person to topic preference is okay, first look at the person ID, then the topic ID, I have the reward. Which means it's actually pretty hard to evolve this, because as soon, imagine you want to add a new preference. Like, so you want to add a preference because some people say, I don't want to be in big groups. I want to have a preference for small groups. With the older one, it's easy to implement, right? Just a new subclass with a new rule. Here, you have to figure out how you can implement that as an array. And then you have to actually modify the scoring method, because it's not self-contained anymore, right? We've completely forgotten about object orientation or anything. Everything's in the score method. You might also notice the extremely ugly fact that because the schedule is mutable now, I have both the current score and the score that's been cached when I've created the schedule. Which is interesting because in practice, when you run the improvement, typically the first few attempts are easy to improve, but after a while you got a lot more attempts where it doesn't improve the schedule than attempts where it does improve the schedule. So I'd rather, because I'm going to keep an existing schedule for a while, I'd rather cache the score. And my algorithm also gets a lot more ugly, right? The beginning is pretty much the same, but then when I've swapped the persons, so I need to check if my current score is bigger than the score I have cached. If it is, then great, I can do a full copy, because the score is not the only thing I've cached. A simplified version, you can look at the actual code for all the other stuff. So, and otherwise, if my schedule was not an improvement, well, just as before, we had for in the game, we're going to have to unswap everything. The opportunities to fail something here are huge, right? Because you have array indexes everywhere, it's, by experience, really easy to mix it up and look first the topic ID and then the person ID instead of doing the opposite. And you cannot have opaque types here because they're just going to be used as index in arrays. So the compiler has to know those are ints. Really easy to mix it up, really easy, harder to make changes. That's not a great combination, right? However, and this was constant on all computers I tested it on. The all-in version is way faster, like 3 to 4 times faster. Because the scoring is way faster, looking into this matrix is way faster to find the score of someone than go through list and then go through list of preferences. We have a lot of arrays of primitive values, which again can be very easily optimized by the compiler. If you don't know about, so obviously the CPU cache, which is good, but also the compilers nowadays are super good at doing multiple operations at the same time on a vector on an array of primitive values. If you don't know about vectorization, you can take a look. But the basic idea is that a lot of CPU now implements the idea that you can do multiple operations at the same time in a single CPU command. The code's horrible, and honestly, I'm forcing a bit the trait because, yeah, it's not great, but it's still readable. That's a heavily simplified version. Now imagine that on an actual production system, which is going to be much more complex than that. The code is going to become hard to read fast. And sure, you can do stuff to make it easier. You can wrap it in a bunch of pseudo classes, which will only contain methods. You're trying to do macros. You're going to kill your compile time to make it a tiny bit more readable. But it's nowhere as readable as the initial representation. But then again, it's 4 times faster. Okay, where does this leave us? Main takeaways: arrays are fast, mutability is fast. That shouldn't be much of a surprise anymore. It's actually surprising. Mutability is fast for longer than you think it would be. Even if you had to do reverts and stuff like that and complicated stuff when you go back and forth between your modifications and canceling them, it's still better than copying a lot of the time. Arrays are fast, and I mean not only when you iterate through them, even as sets, for very short sets. Like, honestly, when I check the tipping points, depending on your computer, depending on your version and stuff, it's somewhere between 10 to 20 elements. Over 20 elements, you're almost always better with a hash set. Below 10, it's likely that just an array is going to be better. Don't be afraid to use macros when necessary. And that's something that's easy to check out actually in the bytecode. So easy optimization to check. And again, you're sacrificing some compile time. Okay. Obviously, do not do that on your whole application. That's why the monitoring part at the beginning is so important. You need to figure out what your hotspot is. You optimize your hotspot, but please do not transform your entire application to become a bunch of arrays of ints and doubles and matrices, because that's going to be horrible for you in the future. Also, again, I'm repeating myself, but please benchmark and monitor with production code and data, because that is going to influence a lot. The JVM has something called speculative optimizations, where it's actually making guesses about, hey, actually, given the data, that part of the code is never executed. Okay, so I can completely optimize it out. Except sometimes, after a while, it realizes, okay, I was wrong. I need to put it back. This is the kind of things you'll only see if you're using production data. A few reads quickly, if you want to learn more about a bit about the theory behind all of this. The first one's a very short article, and easily read article about how does the JIT compilation works. All of the links are also in the README of the benchmark page, repository, sorry. The first one is going just to, it's not very long. It doesn't go to any depth, but it's going to give you a lot of keywords about what's happening in the JIT compiler. And then you can search for those specific keywords to get more information, to get, okay, what exactly does that mean? The second one is kind of the opposite. It goes extremely in depth about what happened in modern CPUs. Unless you're a CPU programmer or a driver programmer, most of it, I did not understand most of it, honestly. Maybe some of you are better than me in CPU programming. That's entirely possible. That's not all my area of expertise. But just skimming it is going to give you a good idea about where modern CPUs are right now. But what kind of optimization you can expect and what kind of stuff is going to improve your situation. And the last one is a short article that was done about the very first thing I showed, you know, how to implement a C-style for loop in Scala, pretty much comes from there. And it goes a bit more in depth about, okay, what's so bad about Scala's for loop and the way it ends up in the bytecode. So again, you can take a look. It's actually potentially worse than what you think when you have something like imbricated for loops, non-local returns, etc. Those things are horrible when they turn out in the actual bytecode. There's a lot of things I could have talked about as well, but I'm kind of limited by time. I did not talk about multi-threading. I did not talk about a bunch of libraries that can help you. You're going to have to find that on your own, or I'm, of course, available for any questions. The QR code at the top is corresponding to the repository.
Thank you. Very interesting. You didn't mention I saw an article on causal profiling.
On, sorry?
Causal profiling. It's a technique where you can add some gap between calls randomly, and then study after where the gap are significant during the test, so find the parts that should be optimized.
Okay, I did not know the term, so I'll have to take a look, honestly.
You look for causal
profiling,
and I will be very interested to know if it's something that should be used, maybe used, I don't know.
Honestly, I cannot answer because I do not know. I'll have to check it out. But thanks for the suggestion.
Any other question? Thank you.
It's good.